I want to talk technically about the definition of work. And although yesterday we gave it a kind of a verbal definition, and I do want to remind you about that verbal definition, that it is the method by which you change something's energy. There's a lot more that we have to deal with when it comes to it than just that. One of the whole goals of this unit is to try and get away from having to do the net force analysis like we've done in the past. The whole having to break a problem up into its component vectors and deal with the direction of everything and assign something positivity and negativity. One advantage of using the concept of work to solve a problem is that work is a scalar. And because it's a scalar, the direction part isn't as important any longer. And a lot of the stuff that we talked about in dealing with forces was largely about direction and drawing a free body diagram and breaking it up into the x direction and the y direction. Dealing with work, we don't have to do that. But there are some things we have to do to be careful, and that is understanding that work is the product of two vectors. And I tried to impress this upon you yesterday. I don't know how successfully I was able to, but this is not a standard multiplication. This is called a dot product, also known as the scalar product. In your notes, I want you to get down that this takes two vectors and produces a scalar. It specifically tells us how much of the force is in the direction of motion. I think we talked about that a little bit yesterday, but we're going to be a little bit more functional today. So technically, to do a dot product, I'm going to write it like this on purpose to make you understand what the process is supposed to be telling us to do. Those bars are not absolute values. When you put bars on either side of a vector, you're actually saying to take the magnitude of the vector. So you just want its size. So to calculate work, you take the magnitude of the first vector, the force, and you multiply by the magnitude of the second vector, the displacement. So for those of you who don't remember what the word magnitude means, it just means size. But they'll use the word magnitude on the test, so you need to be capable of understanding that. Anytime you see the word magnitude, just use the word size. This part is, well, let me say it different. This is now, I don't know if it's obvious to you or not, but the cosine is important in that. That's the part that tells us how much of the force is in the direction of motion. So this is the angle between the force and the displacement. So if we draw the picture, and we drew one yesterday, but it was kind of messy, so let's try and be more careful today. Here's the floor, here's our cart. And we apply a force. Say this way, oh, not like that. Apply a force, say this way on the cart. And because of that force, maybe the cart moves this way with some displacement. This dotted line, it represents the direction of the displacement. So this angle would be the angle between the force and the displacement. And again, we talked a little bit about this yesterday. I'm just trying to recap. So this kind of brings us right to where we were at the end of class yesterday, right? This kind of stuff was in your notes, pushing the cart and all. Right. So let's start with what I want you to deal with today, which is just a little bit more than we dealt with yesterday, but your calculator is probably going to need to be involved a little bit. So imagine we have just a box and we're going to pull the box like this. And let's assume the box is experiencing a frictional force. Can you identify all the forces that are likely acting on the box from our past experiences? So can you name a force that's not already been drawn? So we got a gravitational force downwards. Another one? Normal. So we'll have a normal force. And I'm going to be careful not to draw the normal force as big as the weight because I'm pulling slightly upwards on the box. And what else? Friction. So these are the forces that act on the box. And let's say that due to these forces, the box slides this way, some distance. Which of these forces do work on the box? Based on the drawing, I think you can kind of get an idea. In order for a force to do work on the box, that force has to have a component in the direction of motion. So when we consider the definition of work, remember work is the size of the force times the size of the displacement times the cosine of the angle between the force and the displacement. Any force acting on an object can do work, but it's important that you understand it can do work. It doesn't mean it is doing work. For example, is the normal force doing work? Now, it's clearly got a force with some magnitude. The box clearly has a displacement. Why isn't the normal force doing work? Right, there's no component in the direction of motion. In fact, what's the angle between the normal force and the direction of the displacement? 90. Cosine of 90 is? Try it. Put it in your calculator. Make sure you understand why this works the way it does. Cosine of 90 is 0, right. So it's not that there isn't a force, it's that there's no component of the force in the direction of motion. The cosine of the angle is 0. So does the weight do any work? Not if the box is sliding sideways. What is the angle between the displacement and the weight? What is that angle? 90, so cosine of 90 be 0 again. Is the applied force doing any work? Yeah, there's a component of that force in the direction of motion. Is the friction doing any work? This one's more complicated. What is this angle? What's the cosine of 180? So this force does work. In fact, it does negative work. And I'm hoping that some of this kind of will make sense. So hear me out. This force is actively trying to pull the box to the right. Agreed? Now, I would say that if the box has an initial velocity of 0, this force is trying to change that. It's trying to change the kinetic energy of the box. Trying to make it go faster, I would assume. This force, is it trying to help the box go forward? No, but that doesn't mean it's not doing something to the box. If this force is trying to make the box go forward, this force is trying to prevent that from happening. So while the work done from the applied force is positive, the work done from the frictional force going to be negative. Ultimately, what that means is there will be a certain amount of net work done. That'll be the total amount of work done on the box. There's the work you apply to the box, and there's the work that friction does on the box. If that work is positive, then there'll be an increase in kinetic energy. If that work is negative, then there'll be a decrease in kinetic energy. And obviously, if the net work is zero, there's no change in the kinetic energy of the box. Now, it's all about energy. So let's work an example, if you don't mind. Take examples like we did. I want to see if you can kind of work out the problem. So we'll start with a 5 kilogram box experiencing a 100 Newton force. Let's be more reasonable. Let's say 20 Newton force at an angle of 30 degrees. And let's assume it's experiencing 3 newtons of friction. There are 4 forces acting on the box. We know we have work that's being done by the 20 Newton force, work that's being done by the normal force, work that's being done by the weight, and work that's being done by friction. Let's calculate how much work is done by each of the forces on the box. Now, I think this will be relatively straightforward, but in case it's not, again, work is the size of the force times the size of the displacement times the cosine of the angle between them. So let's try the first one. Looks like we're going to need something that I didn't give you, right? What are you going to need? You know how far the box slid during this process. Let's say the box slid a total of 3 meters. So we're just talking about sliding something across your table. So the work done by the 20 Newton force will just be 20 times 3 times the cosine of 30 degrees. Although we don't know it, can we already kind of make an assumption that I don't have to worry about the work done by the normal force? Oops, not 90. Or sorry, it's not 0, it's 90. Because we're going to have that cosine of 90 there. Although I wrote it down, in this case it doesn't really do any work, does it? Now we know the weight, it's 50. We know the box moves 3. But again, does the weight do any work on the box? Yes, no? No, cosine of 90. But friction does work on the box for sure. It's a 3 Newton force acting for 3 meters at a cosine of 180 degrees. So this should be pretty straightforward. I assume you did cosine of 30 and then did times 3 and times 20. All right? What do you get for the amount of work done by the 20 Newton force? 9? Yeah, I'm thinking it's going to be like 50 or something. So 51 point what? 51.9, so we'll say 52, that'll work. And that's newtons times meters, so that's joules. The next two are clearly 0, so I don't have to worry about them. The last one's just -9 joules. So each force has done work on the box. Now, if we want to know if the box's energy increased or decreased, I think we know the answer. We know that the net work done on the box is going to equal the sum of all these. So 52 minus 9, or 43 joules. Now, this is just calculating how much energy was given to the box, all right? But we know more than this. We know that any energy left with the box changed something about the box's energy. Now, there's multiple ways the energy of an object can be changed. So I want to be really clear. In this case, the box has more energy than it had before, but it was being slid sideways. This is something where you will have to make a reasonable deduction about what changed about the box. Can we kind of agree that over the course of dragging the box across the floor, the box is now over here, moving this way? In fact, it's not arbitrary. This has to equal the change in kinetic energy of the box. You should be able to tell me how fast the box is going. Try it, please. We talked about kinetic energy yesterday. See if you can't use what we talked about yesterday without me having to spoon feed it to you to figure out how much the kinetic energy of the box changed and therefore how fast the box is going. I'll give you a hint in case you didn't write it down. Kinetic energy is 1/2 mv squared. I'll call on one of you in just a minute. I'd like you to consider that a week ago, we would have had to use forces to do this problem. You guys remember how we did forces and stuff? To do forces to do this problem, you would have drawn a 3-body diagram. Something like this. You would have been told to put a coordinate system on this. You would have broken up one of the forces into its components. And you would have had to decide whether this was a first law problem or a second law problem. Hopefully you would have decided that, well, in the x direction, it's a second law problem. You guys remember all these steps? Now, this would have given us, say, 20 cosine 30 minus 3 equals 5a. It wouldn't have told us how fast the box is going, but it could have given us the acceleration. Do that for me, will you, please? What's the acceleration here? I'm going to pick one of you, so check with somebody next to you. See if they have the right answer, because I'm just going to call on somebody kind of random, like, to be mean. Reagan, does he have the right answer? Oh. Anybody else get 2.8? Really pretty good. That's the right answer. A lot of you. We'll go by democracy. Now, you'll notice we never got 2.8 as one of our answers because we were never asked for the acceleration before. You were asked to figure out how fast the box is going. So we could get how fast the box is going. We know the initial velocity was 0. The final velocity was what we were looking for. The displacement was 3. Can you pick a motion equation and figure out how fast the box was going? If you don't know which one, I'd probably use v final squared minus v initial squared equals 2a delta x. I'll give you just a second, but figure out what the final velocity is. Let me guess, same answer? It really better be, because this stuff all has to work together. So when you work it out, yeah, you should get 4.1 meters per second again. And you most certainly do. Now, neither one of these methods is right or wrong. But you'll notice, in order to figure out the velocity on the right side, you just found the total work done and set it equal to 1/2 mv squared. To find the same information on the left side, you had to analyze, apply a coordinate system, break into components, and then get the acceleration, and then use a motion equation to figure it out. Although it looks like there's more work on one side than the other, I'd say that this work is probably easier to do. Let me give you kind of an overview here. Work problems. They're really good at A, finding energy. But also they're really good at dealing with velocity. They're also really good at dealing with or finding displacement. So I'm going to make this the pro list. So if your problem asks for how fast something is going, work might be the best way to go. If it asks for how far something went, work might be a good way to go. But there's a con list here too. Work problems are not particularly good at finding an individual force. It can, it's just harder. So if your problem asks you to find a force, I'm not sure this is the way you want to go. It can be done, but it's not always the ideal way. Second, they definitely don't deal with time. Nothing about this ever said how long it took. And it really doesn't deal with acceleration. So if you have a problem that's about velocity, you probably want to look at work. That's a good way to solve it. If you have a problem that's about how long does something take, this is probably not going to do it. It's not ideal. There'll have to be extra steps afterwards to get to that answer. So when we deal with work and energy problems, a lot of the time we're going to be asked to find something that deals with its energy or how fast it's going or how far it went. So if the problem asks how fast is it going after something happened, work might be the right choice. Remember, when you guys go to take exams, you'll have to choose on the fly, is this problem going to be best to use work to solve or best to use forces or best to use something else? So I'm going to start making these kind of pro-con lists to help you kind of determine, well, what's my problem asking for and what kind of things do I have? So let's talk about a couple of other problems. I'm going to do a problem that is kind of silly, but I want you to consider it anyways because it's going to lead to something else. I have a box. It is, let's go back with our 5 kilogram box. And I'm just going to drop it 3 meters above the ground. Okay? Can you find how much work is done on the box by all the forces acting on the box? Assume there's no air resistance. So we'd start by asking, what forces are acting on the box? Definitely has weight acting on the box. Weight's acting downwards on the box. And how big is the weight? 50 newtons, right? 5 times 10? Now, if I wanted to figure out the work done by gravity, then all I would have to do is figure out what is the size of the force acting on the box times the displacement of the box due to gravity times the angle between the between the force and the displacement. So, force of gravity acting on the box is how much? 50. What's the displacement of the box? What is the angle between the force and the displacement? Well, the box is being pulled downwards. Is the box going downwards? So what's the angle between downwards and downwards? Yeah, 0. Don't make it hard. So the work done by gravity, 150 joules. Are there any other forces that act on the box? If not, that means that the net work done on the box is 150 joules. Now, more importantly, that will equal the change in kinetic energy of the box. Now, I know that we've done problems where we've just dropped stuff before, and we've said to ourselves, well, if I want to know how fast it's going, I wouldn't do this. I would just use a motion equation, because we've done motion equation problems. Please trust that there's something important that's going to happen here in the next 2 days that's going to make this very worthwhile. So figure out, using energy, how fast the box is going, please. It's not a big deal. We're going to set 150 equal to KE final minus KE initial, which is still 1/2 mv final squared minus 1/2 mv initial squared. Assuming it was dropped from rest, I get 150 equals 1/2 times 5 times v final squared minus 1/2 times 5 times 0 squared. Now, I don't want to belabor this. It's not going very fast or anything. But this is how you'd use energy and work to figure out the same thing we did with the motion equation. Okay. Now we're going to try one more, and I'm really hopeful that you guys will pick up on something that's going to happen here, okay? Did Mr. Shelton not add right? Is it plausible Mr. Shelton can't hit his own buttons on his calculator? It's so plausible. It's not rare. Yeah, you're right. That's good, though. I'd hate to produce a video that's got the wrong answer in it. So Mr. Shelton can't hit the buttons on his own calculator. That's why he's not going to do well in the next test. 5. I believe it might be true. That means Mm-hmm.
I got 7.75. Yeah.
We should be concerned. Well, he should be concerned. You guys don't have to care. All right. So it's angled a little more than I want, so let me tune it down a little bit. There we go. Something like that. All right. Let's say again that this is 3 meters. Okay? And let's just say that this is frictionless for this particular problem. All right, no worries. Now, this is 30 degrees. And we still have the same box, 5 kilogram box. Or was it 50? 5 kilogram box. There we go. The box is going to slide down the ramp. And I like to figure out how fast it's going at the bottom of the ramp. But I want to do so using work. Okay? So, is it clear to you that the box is going to go this way? Oops, not like that. It's going to go this way down the ramp. Okay? And this is going to be hard for you guys to kind of pick up on, so let's see if we can do this. I want to find out how much work is done by gravity. Because if we look at all the forces acting on the box, there are only 2. There's gravity, which acts straight down, and there's normal force, which acts perpendicular to the box. Everybody follow along with that? All right, we've done this problem before. If I want to find the work, well, there's the possible work done by gravity and work done by the normal force. To find work, we need the size of the force times the size of the displacement times the cosine of the angle between the force and the displacement. Everybody okay so far? All right, well, I don't know what the normal force is, but do I need the normal force? I want you to look closely. What is the angle between the normal force and the direction of the displacement? 90. You guys see that this angle here, this angle here, which is the angle between the normal force and the direction of displacement, that's 90 degrees, right? So that means the work done by the normal force is going to be 0. Now we do know what the weight is. It's 50. Do we know what this angle is? Because this is theta. I'm not sure if we have it, but I think we have enough information to get it, right? Wouldn't that angle have to be the same as whatever angle this triangle is here? If this is 30 right here, what does this angle have to be? It's got to be 60. So wouldn't this angle have to be 60? All right, so we have our cosine. Cosine, 60 degrees. Delta x, that's going to be tough. But I think we can get it, right? I mean, don't we have the height here is 3 meters? So couldn't we use that to figure out this length? In fact, I think sine of 30 is going to have to be hypotenuse 3 over whatever this is, delta x. So you guys are smarties. What is delta x then? I don't think so, because I think sine of 30 is 0.5.
Yeah, that's not.
Okay, so I think it's going to be 6 meters. All right, so there we go, 6. That's it. How much work was done by gravity?
$150.
150. Weird. No, you're not doing it wrong. That's it. That's the right answer. It doesn't matter that the box slid down the ramp or went straight down. And this is going to be hard for you to understand at first, but remember when I said that fundamental forces are somewhat special? That they do things that are somewhat unusual? When it comes to talking about fundamental forces, they are path independent. What that means is the amount of work done doesn't matter whether the box went straight down or went down the ramp. The same amount of work is done in both cases. In fact, all that matters really is how high the box was compared to where it lands. This is gonna come back to help us because I want you to think about this for a minute. If I ask you how fast is the box going when it reaches the bottom, you know that you already have the answer, right? Although Mr. Shelton couldn't hit the buttons right, it's got to be 7.7 again, isn't it? Because we had the same amount of energy as before. The same amount of work was done as before. What you might have given you some good reason. Would you agree? And be a problem, we could have used forces, couldn't we? We could have found the acceleration and used forces to figure out the velocity. The surprise to learn is that even if the ramp looked like this, and we placed the box, up on top of the ramp here, if this were 3 meters, the same amount of work would be done by gravity, even along the curved surface. Now, we're going to try and prove this to be true, but I've already deal with stuff like, stuff we couldn't deal with before. Like, there's no way we could do that here. Right? You see that force is always changing the whole way down the track, right? Because, right now, although the weight is one direction, the normal force is going to be changing all the time. So the component down the ramp is going to be changing all the time. You guys see that okay, right? But we'll be able to prove that it won't matter. The same amount of work was done, meaning when the box makes it to the bottom, it will have acquired 150 joules of energy at the bottom. In fact, most of our problems will be path independent. That's the phrase I want you to start using. Path independent. Any work done by a conservative force is path independent. Any work done by a conservative force is path independent. There are lots of conservative forces. The word conservative isn't fundamental. There's lots of conservative forces. So although all the fundamental forces are conservative, there are other forces that are conservative too. This is for conservative forces. We have time for one more thing, and then we'll be done. All right, same problem as before. 30-degree angle here. This is 6 meters long. And you are going to push the block up the ramp with some applied force at a constant speed. Okay, this is a net force equals 0 problem, correct? Because we're going to push the box up at a constant speed. Does that make sense? So our applied force is in the direction that we want to go, and the whole ramp is 6 meters long. I want to know how much work is going to be done by the applied force. Now, I know that for you guys, there's a lot of work to be done here. So I'm going to do some of that work for you. How many forces are acting on the box besides my applied force? 2. So there'll be the work done by, there's the force of gravity, and there's the normal force, correct? Now I want the work done by the applied force, just that one. We already know that the displacement is going to be 6, and the angle is going to be 0 degrees because we're pushing in the direction that the box moves. But we need to know how much force we apply to push the box up the ramp. You guys getting that in your notes? In this case, you might have to do a force problem first to figure out how much force I need to push the box up the ramp.